What we're going to talk about here is something called the difference quotient. This is something that shows up in Algebra 2, Algebra 2 Honors, and pre-calculus, and sometimes in trigonometry classes. What you're going to do basically is evaluate this function using something called the difference quotient. So I'd like to just do a little mindless template here. See the minus sign? I put a minus sign on top and an H on bottom, and then I try to figure out what goes in the back of this minus sign. And I always bracket it up if there's more than one item for f of x. And what goes back here is f of x. F of x equals x squared plus 4x. And then this is where it gets a little confusing to some people. This function does not go up front. This function with x plus h in for x goes up front. So I set up this template, something squared, that means x squared, plus 4 times something. Now, the something is going to be this x plus h. So I pop in x plus h wherever there was an x up front. Now I have some foiling to do and some distributing to do, and I have to distribute the negative also, and that's a big mistake. In all these courses, people forget to distribute the negative. So I'm going to FOIL out x plus h, the quantity squared, and that's going to give me x squared plus 2hx plus h squared. I know a lot of people think it was just x squared plus h squared, but if you were to FOIL it, you get an hx and an hx twice, so that gives me 2hx. Then I distribute the 4, so that's plus 4x. Distribute the 4 plus 4h minus x squared, and don't forget, minus 4x all over h. Now I'm going to look for stuff to eliminate. I'm going to combine like terms. So x squared and negative x squared cancels out. Also, the negative 4x and the 4x cancels out. And that leaves me with 2hx plus h squared plus 4h all over h. Excuse me. Getting close to the end here. Now all I have to do is factor out an h from the top. So when I pull an h out, that's going to give me 2x plus h plus 4 all divided by this h. And they cancel out, and my final answer, lo and behold, is going to be 2x plus h plus 4. And that's the difference quotient, in a nutshell. We're going to do another difference quotient, but notice this time, it's actually calculus. With this limit as h goes to 0, this here is one of the first things we do in calculus, is the difference quotient defined as a limit. Now, what that's going to do is break this down a little bit better than when we just did the Algebra 2 version or the pre-calculus version of the difference quotient. This is actually the definition. It's called the definition of the derivative. And same thing, but if you're a little technical about it, you want to write this little designation, the limit, as h approaches 0. Some people say as h goes to 0, in front of every step. I'm going to do my same template, big division bar with the minus sign over h, and now in the back of the minus sign, I want to put what f of x equals. Now in order to do that, I want to put some parentheses around it. And then, again, I want to set up this template up front. So I'm going to put 2 times something squared, that's my 2x squared, plus 3 times something. And that something, running out of room there, that something is going to be the x plus h. So I have to place the x plus h in both of these templates. Now again, it would be really nice to know what the quantity x plus h squared is. And I just happen to know it off the top of my head. It's something you want to, I wouldn't say commit to memory, but if you do it enough, you'll remember that x plus h is going to be x squared plus 2hx plus h squared. I'm going to distribute that 3 plus 3x plus 3h. I'm going to distribute that negative minus 2x squared minus 3x. This is getting a little long. All over h. It's not that tedious, though. It goes pretty quickly once you get the hang of it. I'm going to bring down this designation limit as h goes to 0. Now I'm going to distribute that 2 across. So that's going to give me 2x squared plus 4hx plus 2h squared plus 3x plus 3h minus 2x squared minus 3x all over that h. Again, I want to see if stuff disappears, and the clue is to work from the back end. You should start to realize that everything from the back is going to cancel out with a few items from the front. So the 3x and the positive, negative 3x and the positive 3x cancel out. The negative 2x squared and the positive 2x squared cancel out. And that gives me this next line. I'm going to write the word limit again. Limit, as h approaches 0, of 4hx plus 2h squared plus 3h all over h. Now in this line, I'm going to simplify it. I'm going to pull an h out. So when I factor that h out, that will give me 4x plus only 2h. Think about it. H times 4 is 4hx. H times 2h is 2h squared, plus 3, because h times 3 is 3h, all over h. Now the h's cancel out. And one more line, limit, as h goes to 0, of 4x plus 2h plus 3. Now the deal is, what do I let h equal? It says as h goes to 0, so I throw that 0 in for h. 2 times 0 is 0. So this is going to give me 4x plus 3 as my final answer using the difference quotient. I want to do some limits here. That's what we're going to talk about. And these limits we call using direct substitution. Basically, the limit as x approaches 2 of 5x plus 2. You take this 2 and you substitute it in for that variable. And that's going to equal 5 times 2 plus 2, which is just going to be 10 plus 2. And that's going to equal 12. Not too challenging. This one is a little theoretical. This is basically the line y equals 5.
So if I had a line y equals 5 going through there, and that line up there, I'll put it in a different color. That line up there is y equals 5. As x approaches 1, 2, 3, the limit is going to be y equals 5. So the limit of a constant is usually just that constant. So this limit as x approaches 3 of 5 is just 5. You probably don't have to show the work for it.
For number 3, the limit as x approaches 7 of x squared plus 1. I'm going to use direct substitution again. So that's going to give me 7 squared plus 1. Well, that's 49 plus 1, and that's going to give me 50. Again, I'm going to try direct substitution. When I throw a 1 in there, that gives me 1 squared minus 1. So that's 0 on top. And then I throw the 1 in the bottom. That gives me 1 uh-oh.
That's called indeterminate form. Indeterminate. Maybe it's a man. I don't know. But no good. What that means is I have to use a different
method. I can't just do direct substitution for this limit. And I notice this top is a difference of two perfect squares. So that's going to give me x times x equals x squared. 1 times 1 equals 1. And the signs are going to alternate. And then I notice the x minus 1 on the bottom will simplify with the x minus 1 on top. I'm still going to write the word limit as x approaches 1. I still can't do direct substitution. I'll still get 0 over 0. But once I cancel these out, and that would be a hole. There would be a hole located at x equals 1 because they cancel out. I'm going to find the limit as x approaches 1 of just x plus 1. Now notice I can do direct substitution and put the 1 in for the x, and that will give me 1 plus 1. So the limit as x approaches 1 of this is actually going to equal 2.
Another limit problem and another difference quotient. Again, this here is the prelude to calculus. This here difference quotient with the limit as the bottom approaches 0. There's a lot of other great videos, informational videos on this, of where this formula comes from. I just want to work towards the answer of finding the limit as h approaches 0 using the difference quotient of x squared minus 3. So I'm going to copy down the limit. I'm going to be very formal about this. Put my big division bar template. I'm going to throw some parentheses so I can put that in the back all over h. And now what I put in the back is that f of x. So that's x squared minus 3. And then I'm going to set the template up front. Something squared minus 3. So something squared minus 3. Now what do I put in for that something? You should start catching on, and I'm going to put this here x plus h in. That goes directly into that quantity, x plus h. And now I'm going to do a lot of algebra and evaluate this limit as h approaches 0. The limit as h approaches 0 of, it'd be nice to know what x plus h squared is, and I just so happen to do. That's x squared plus 2hx plus h squared minus 3. Distribute that negative, minus x squared. Distribute that negative, plus 3 all over h. Now I'm going to see if anything cancels out. The limit as h approaches 0. Notice if I work from the back, the positive 3 and the negative 3 go away. The negative x squared and the positive x squared goes away. And that leaves me with just plain 2hx plus h squared all over h. Now I can factor an h out of the top. So when I pull that h out, that's going to give me h times 2x would equal 2hx plus h, because h times h would equal h squared all over h. And the h's cancel out. Now I'm going to do this one more time, I believe. The limit as h approaches 0 of 2x plus h. And when I substitute 0 in for that h, I get just plain 2x. Now there's a shortcut to do this. There's a shortcut to do this. Instead of doing all this work using the definition of derivative, you can use something called the power rule. And all that does is you take this exponent and you multiply it by the coefficient up front. And that would give me 2x. And then you subtract 1 from that exponent. So that would be 2x to the first. And this is technically x to the 0. Because x to the 0 is 1. 0 times negative 3 is 0. And when I subtract 1 from that, but 0 times anything is 0. So my answer using the power rule in about 3 seconds is the same as my answer using the definition of the derivative, which takes a little bit longer.
I want to talk about something called the derivative. Now, for each of these problems, I could use the difference quotient, but that's a little tedious. There's a quicker method, and it's called the power rule. Now, you can't always use the power rule, but when you can, you want to implement it. Basically, all you do is you take that exponent and multiply it by the coefficient in front. So 5 times 3, that will give me 15. And then you subtract 1 from that exponent. So that'll give me 15x to the fourth. And a way of saying that you've taken the derivative is not y to the first, that's y prime equals 15x to the fourth. And that's pretty quick. Yeah, you just found the derivative of 3x to the fifth. Now I want to find the derivative of 3x to the fifth plus 2x cubed plus 4. Now this is a little theoretical. Technically that's 4x to the 0 power. Because from algebra we should all remember that anything to the 0 power equals 1. And that's why when you take the derivative of just the number 4 or 75, it's going to equal 0. So the derivative is 5 times 3, that's 15x, and then I subtract 1 to the fourth, plus 3 times 2, that's 6x, don't forget to subtract 1, squared. Now 0 times 4 is 0. Another way to say that you've taken the derivative of this is to say dy dx. But it's just quicker to put y prime. Now this one's a little bit more involved. We can implement something called the quotient rule because these are quotients, they're fractions, or we can play around with the exponent in order to make it quicker to find the derivative by using the power rule. So I want to rewrite this, not y prime, y equals x to the negative 2. Remember, laws of exponents state if I bring him back up, his attitude, his exponent is going to change to negative. Plus
x to the negative 12th. Again, I brought this x to the 12th upstairs, and when I do, the exponent changes. Now, 3x to the 5th, we've been finding the derivative of that. It stays the same. It's not a fraction. So I'm going to say y prime equals negative 2x to the negative 3rd, because I have to minus 1 from the exponent. Negative 12 times 1 is negative 12x minus 1 to the negative 13, plus 5 times 3 is 15, x minus 1 to the 4th. Now, some people wish for you to rewrite this without any negative exponents. So what you might want to do is the negative 2 stays upstairs, and the x to the negative 3 goes on the bottom, and when it goes downstairs, its exponent changes to positive. Minus 12 over x to the 13th plus 15x to the 4th. To find the derivative of this expression, it's not a polynomial expression because I have negative exponents and radicals. It's very difficult to use the power rule on a radical, so what you'd like to do is change that radical form into a rational exponent. I have a cute little story that goes with this. That's a bucket, and since the 3's in the bucket, the 3 goes on the bottom, and then the 2 will go on the top. Plus, well, this guy's downstairs. This is 1 over x to the 4th, so I'm going to bring that upstairs, and when I bring it to the numerator, his exponent changes to negative. And then add 3x to the 4th. Now I'm ready to differentiate this or find the derivative of this expression. So the derivative will equal, that's not y to the 1st, that's y prime, equals, well, I do 2/3 times the number 1 out front. So that's going to give me 2/3 x. And don't forget I have to minus 1. But a little trick is to write 1 as 3 over 3. And that will give me a common denominator. So that's going to give me to the negative 1/3 power. The exponent using the power rule times the hidden 1 up front. That's going to give me negative 4x. Don't forget I subtract 1 to the negative 5th plus 12x minus 1 to the 3rd. Now, in some schools of thought, they don't like negative exponents. So what we're going to do, just in case, if you're required to, is change these negative exponents to positive exponents. So the 2 is on top, so he can stay there. 2 over 3, x to the 1/3, minus 4 over x to the 5th. If you write this as a fraction, the x to the 5th is next to negative 5th, goes to the bottom, plus 12x cubed. Now, a lot of times you'll be done with the 2 over 3x to the 1/3, 4 over x to the 5th, but some schools of thought don't like you having a rational exponent. So dy dx equals 2 over 3. Now what's in the bottom is a 3, so that goes in my bucket. X, and I don't need to put the 1 there, but I will. Minus 4 over x to the 5th plus 12x cubed. It depends on who you're working with, where they allow you to stop. Some schools allow you to stop there. Some make you go to this step. And then in really extreme cases, they'll make you rationalize or unrationalize, whatever you want to call it, everything to get it to look like that. What I do is find derivatives of trigonometric functions. So the derivative of y equals sine x, and most teachers or professors expect you to commit this to memory, but there's usually somewhere in the book a list of derivatives. So you can seek through this and then, oh, there it is. The derivative of sine x is just cosine x. So I shouldn't put equals there. I'll put y prime, I'll put like a hyphen, semicolon. Y prime equals cosine x. So by logic, y prime, the derivative of cosine, you think would be sine x, but it's not. It's not. If you look at the derivative table, it's actually negative sine x. Sometimes you get confused and you forget which one's positive or negative. Derivative of tangent x, well, again, I'm going to go to my list of derivatives, and that's actually secant squared x. So y prime, the derivative is secant squared x. The derivative of 5 sine x, well, is going to be 5 cosine x. So that's going to give us y prime equals 5 cosine x. And the derivative of 8 cosine x, well, the derivative of cosine x was negative sine x. So that's going to give me the derivative y prime equals negative 8 sine x. Now, in order to do this one, you have to realize that sine x squared equals sine x times sine x. It's not the same as saying sine x squared. No, it's the same as saying sine x squared. So in order to find this derivative, I'm going to have to use something called the product rule.
To use the product rule, after you've split this into a sine x times sine x, you want to label this first part as something called u, and the second part as v. I split it down the middle, and I have 2 elements. I'm multiplying sine x times sine x. That's where the word product rule comes into play. Now, product rule is right here. If you're multiplying 2 elements, it's u dv plus v du. So I'm going to write that down. U, the first element, times the derivative of the second element, plus v, the second element, times the derivative of the first element. And I have a little graphical organizer that I implement for this. I put u equals here, v equals here, the derivative of u equals here, and the derivative of v equals here. Now, u is just sine x, and v is sine x. Kind of strange. The derivative of u is, or the derivative of sine x is cosine x, and the derivative of sine x is cosine x. Now I have to do u times derivative of v, so I do sine x times cosine x. Sine x times cosine x plus v du. That's going to give me sine x times cosine x. And since I have two of the same terms, like terms, I'm going to combine like terms. That should give me dy, the derivative, dx equals 2 sine x cosine x. And that's my final answer, using the product rule.
Find this trig derivative by using something called the chain rule. For number 6, I used something called the product rule, and I rewrote the trig function as cosine x times cosine x. That's how I did this process in number 6. But now I want to rewrite it like this, as y equals the quantity cosine x squared. That means cosine x times cosine x. Now I'm going to use something called the chain rule. And the chain rule is sort of the product rule, but with a little extra touch. And here's the deal. After I take the derivative of this big quantity by doing the power rule, 2 times the hidden 1 up front, so that's going to give me y prime equals 2 times the hidden 1 up front. That's 2 times that quantity, cosine x. Don't forget the minus 1 to the first power, but I don't need to write that. After I do that, then I have to take the derivative of the guts. And the derivative of cosine x, I believe, is negative sine x. And I'm not quite done. I'm going to spruce this up a little bit. So the fancy-looking derivative, dy dx, is actually negative 2 cosine x sine x.
What I want to do here is some more power rules. So this is advanced, I guess you'd say it, for this book, I would call it advanced. I have a fraction with a cube root of x to the 4th in the bottom, and I really can't use the power rule in that because I don't have it written in exponential form, or to the power of something. So I'm going to rewrite this in exponential form. So that's going to equal 1 over x to some fraction. And notice the 3 is in the bucket, so what's in the bucket goes on the bottom. And the 4 is there, that goes on top. So now I still can't use the power rule because I have a fraction. In order to implement the power rule, I want to bring this upstairs and just rewrite it as x to the negative 4/3. And now I'm going to do the power rule. Y prime is going to equal negative 4/3 x, and now I have to minus 1 from that. So I'm going to write 1 as 3 over 3, and that gives me to the negative 7/3. And again, there's a couple of different ways to rewrite this.
You might have to, or you might want to rewrite this as dy dx equals negative 4 over 3x to the positive 7/3. Then again, you might want to rewrite that as dy dx equals negative 4 over 3. I'm going to put my radical here, x inside. Now the 3 goes in the bucket because it's on the bottom, and the 7 goes here. Some people put the 7 outside. Some people continue to simplify this because that power is greater than that. You can simplify it a little bit further. dy dx, getting a little tedious. Negative 4 over 3 to the cube root of x to the 6th times x to the 1st, because 6 plus 1 is 7, you add exponents. And then I'm going to bring that outside. So dy dx equals negative 4 over 3 x. Now the cube root of x to the 6th is x squared. Cube root x. And if you're taking a multiple choice test, you might have to keep simplifying until it matches the choice that you're given. So they say multiple choice. Some people think that multiple choice is easier. It's actually a talent to have to recognize what you're given. And you know how cruel they'll be. They'll make something slightly different in one of these to tempt you.
The power rule derivative, what I'd like to do is rewrite this as a rational exponent. So that's going to equal x over, there's a hidden 2 inside and a hidden 1 there, so that's going to be x to the 1/2. And then I'm going to bring him upstairs. So that's going to give me x to the 1st times x to the 1/2, negative 1/2. And now I just add exponents, and that's going to give me equals x to the 1/2, because 1 minus 0.5 is 0.5. So now, that's not my answer. That's what I can use to find the derivative. So I have x equals x to the 1/2. And to find the derivative of that, I'm going to use the power rule. So I'm going to do 1/2 times the 1 in front. So the derivative is going to be y prime equals 1/2 x. Don't forget to subtract 1. But I'm going to write 1 as 2 over 2. Negative 1/2. Again,
some teachers will let you stop there. Others will make you persevere. So it's going to be 1 over 2 x to the 1/2. And some teachers will let you stop there, where other teachers will make you continue on. dy dx equals 1 over 2 radical x. Now, notice the 2 is on the bottom, so that goes in the bucket. But you don't have to put that 2 there. If there's no 2 there, it's implied that there's a 2. And the 1 goes on top, and again, you don't have to put that 1 there. But that could be your final answer. And that's about as far as you can continue with that particular expression.
Now I want to find the derivative of these two. Again, there's really no numbers to manipulate, so you're probably going to have to at first go to your list of derivatives in the derivative table, and there it is, the derivative of e to the x, wait a while, is just e to the x. Salman Khan from Khan Academy goes into a big lecture on why that is. If you're curious as to why, he will be happy to show you why that's the way it is. But most students just want to get to the chase, and they like taking the derivative of e to the x. Now the derivative of ln, which is the natural log of e, again, I'm going to use my derivative table, is actually 1 over x. So that derivative is going to be y prime equals 1 over x. And they're pretty quick if you commit them to memory. And again, there's other videos out there on YouTube that will explain and actually derive why those are the derivatives of y equals e to the x and y equals ln x.
Hi, I'm on page 6 here, and what I want to do is find the line tangent to the curve at the point 217. So it says find the slope, rate of change. Sometimes it's called instantaneous rate of change of the tangent line at x equals 2. Then we're going to write the equation of the tangent line in point slope form. So first I'd like to verify that 17 is the correct y value. What I would do is I would plug in the 2 and see if that's going to give me a y equals 17. So when I plug in the 2, and sometimes they don't always give you the 17. So I plug in the 2, 2 cubed is 8. So it's going to give me y equals 2 times 8 plus 1, and that's 16 plus 1. And yes, that there verifies that that's the correct point. That coordinate is on the curve, y equals 2x cubed plus 1. So now, what I'd like to do is find the slope at x equals 2. So what the process is to find the slope is you take the derivative of this. So the derivative is not that tough. It's going to be 6x squared. Don't forget I minus 1. And the derivative of 1 is 0. So my derivative of that equation is just 6x squared. Now I want to evaluate that derivative at x equals 2. And what that will give me is the slope of the tangent line at that point. So the slope is going to equal 6 times that value 2 squared. So in this case, my slope is going to equal 4 times 6. My slope is going to equal 24. I have a point, and I have the slope. I have the point, and the point is 217. And the slope is 24. I found that by finding the derivative and evaluating the derivative at that point, x equals 2. So my slope is 24. So now I'm going to use this old Algebra 1 formula, point slope formula, because I now have a point and the slope. And I'm going to label this as my x sub 1, and this is my y sub 1. And just as a reminder to get you back in the y minus y sub 1 equals m times x minus x sub 1. Y minus something equals something times x minus something. Good review. And now I'm going to plug in these values. For y sub 1 is 17. The slope is 24. And then the x sub 1 is going to give me 2. Distribute. So it's y minus 17 is equal to 24x minus 48. And I add 17 to both sides. And then this is going to give me the equation in point slope, not slope-intercept form of y equals 24x. Sorry, 17 minus 48 is going to give me negative 31. Negative 31. And that's my tangent line to that point. Y equals 24x minus 31.
Again, we're on page 6. We're going to find the slope of the tangent line, and then we're going to find the tangent line, the equation of the tangent line at 216 of y equals 3x squared plus
4. First thing I always like to do is verify that that is the coordinate that lies on this curve. So y equals 3 times 2 squared. I plug that 2 in, plus 4. That's going to give me 4 times 3 is 12 plus 4, and yes, that equals 16. Now I want to find the slope of the line at x equals 2. So what I do here is I take the derivative. So the derivative is going to be 6x. Don't forget you subtract 1. The derivative of 4 is 0. And I'm going to evaluate that derivative at x equals 2. And that's going to give me a slope equals 6 times 2 of 12. Now I'm going to take my point and my slope. My point is 216. And my slope is 12. And I'm going to use the point slope formula. Y minus 16 equals 12 times x minus 2. Distribute. 12x minus 24. Add 16 to both sides. And it's going to give me y equals 12x. See. And that's my tangent line to the point 216. Page 7, in a very brief look at calculus, we're going to do something called the product rule. So the deal is, you have this little rule here. So if you have two terms, what you do is you take the first term and then multiply it by the derivative of the second term, and then you add it to the second term and multiply it by the derivative of the first term. So I have a cute little graphical organizer for this. So first thing I like to do is split this down the middle and let the first one equal u and the second one equal v. And I set up this graphical organizer, a u equals, a v equals, and then the derivative of u, du equals, and the derivative of v equals. And it goes pretty quick. The derivative, or x squared, u equals x squared, v equals e to the x, and the derivative of x squared is just 2x, and the derivative of e to the x, we already worked on that one, is just plain old e to the x. Now I do u dv, so it's x squared times e to the x plus v du, e to the x times 2x, e to the x times 2x. And as I said before,
Sometimes they'll get away with that as your answer, and other times they'll want you to spruce it up a little bit. Notice I can factor out an x and an e to the x from this expression, so I'm going to pull out an x times e to the x, and that would give me x plus 2. So sometimes your answer might look like this, or they might want you to work a little further, and it would look like that.
for my second problem, I have x squared times ln x. I'm going to split it down the middle and let x squared equal u, so u equals x squared, and ln x equal v, so ln x is v equals ln x, and then the derivative of u is just going to give me 2x, and the derivative of ln x is 1 over x. Now I'm going to implement the product rule, which is u dv plus v du. So u dv, well that's kind of strange, x squared times 1 over x would give me x squared over x plus v du ln x times 2x. And I'm going to just make this look a little crisper and simplify that.
That would give me x plus 2x times ln x. A lot of times they like to put that out in front of the ln. And that one should be your final answer. Sometimes they might make you factor out the x, but I think we'll get away with that.
Our third one from page 7, sine x cosine x. I'm going to split it down the middle, let this equal u, let this equal v, u equals, v equals, du equals, dv equals, and u in this case is just sine x. V is cosine x. The derivative of sine x is cosine x. And the derivative of cosine x, don't forget, it's negative sine x. Now I'm going to implement the process u dv plus v du. U dv is actually negative sine x squared. Sine x times sine x. Times, plus cosine times cosine. That's going to give me cosine x squared. And that's my answer. I can't combine them at all. That's not going to equal 1 because that's cosine squared x minus sine squared x.
They might want you to write that first. So they might want you to rewrite it as cosine squared x minus sine squared x. And that should be your final answer. They probably won't want you to factor it.
We're on page 8, and what we're going to do here is something called the quotient rule. The quotient rule happens when you have a fraction. That's the quotient. So we have this cute little saying, low d high minus high d low over the denominator squared, it must go. So I'm going to designate
X cubed minus 1 is low. So x cubed minus 1 is the low, and the high is going to be x squared plus 3. Now the derivative of the high is just going to be 2x, and the derivative of the low is going to be 3x squared. And now I want to set up this little template with a minus sign, because it's going to be low d high minus high d low. So low d high, that times that, is going to give me x cubed minus 1 times 2x minus high d low. This quantity times 3x squared. So that's going to give me x squared plus 3 times 3x squared. And now all I do is put it over the denominator, the bottom, x cubed minus 1 squared. And that's your answer. Sometimes they'll have you spruce it up a little bit, but for the most part, they let you get away with just that. Number 2. Again, the high is going to give me 2x minus 1. The low is going to give me x squared plus 4. The derivative of the high is just plain old 2. The derivative of the low, the d low, is 2x. I'm going to set up my template with a minus sign, and it's going to be low D high. I might distribute that. That's going to give me 2x squared plus 8. 2x squared plus 8 minus high D low. I might distribute that. That's going to give me 4x squared minus 2x. All over the denominator squared it must go. So x squared plus 4 squared. I think I can simplify that a little bit more. Further simplifying this, 2x squared minus 4x squared, well, that's negative 2x squared, plus 2x, plus 8, all over x squared plus 4, the quantity squared. And that's it for number 2. Now number 3 looks a little bit more daunting. I'm going to set up my high, and my high equals x squared plus 2x. My d high would equal 2x plus 2. My low would equal e to the x plus 1. And the derivative of my low, my d low, would equal just plain old e to the x. Now I'm going to implement the process, low d high minus high d low. Over the denominator squared, it must go. Low d high, well, I'm not going to distribute that. I'm just going to leave it like it is. So I'm going to set up 2 quantities. And my low is e to the x plus 1. And my high is 2x plus 2. Minus high d low. Low d high minus high d low. That I'm going to put the e to the x out front. It just looks a little bit more crisp, I'd like to say. X squared plus 2x. All over the denominator squared, low, it must go. So that's e to the x plus 1, that quantity squared. And that's number 3 from page 8. Page 9, we're going to start something called the chain rule. And usually they have this formula written out for you somewhere in the back of the book, this template, this idea of what the chain rule obviously is. That's a little complicated. I'd rather just work on some examples so you get a feel of what you have to do. It's basically the power rule. Well, 4 times 3, well, that's 12. And then this is x squared plus 9 still. Don't forget you have to minus 1 to the 3rd power. Now, the only thing different of the power rule is you have to now take the derivative of the guts of that expression. And so the derivative of x squared plus 9 is just 2x. And now you usually are expected to rewrite that to make it look a little bit more professional. 12 times 2x, that would be 24x times x squared plus 9 to the 3rd power. What you don't want to do is use binomial expansion to the 4th power and then distribute by 3 and get this long polynomial. That's not what we're looking for here. We're just looking to get a quick derivative by using something called the chain rule. Don't forget there's a 1 out front. So 5 times 1, that's going to give me 5 times 7x minus 3. Don't forget I have to subtract 1 from that to the 4th times the derivative of 7x minus 3, which is just times 7. So in the end, the derivative is going to equal 35 times 7x minus 3, that quantity to the 4th power. Hey, notice it's not sine squared outside. It's sine of x squared inside. So I want to take the derivative of sine, which is cosine. But now I have to take the derivative of the guts, which is 2x. Now, I'm not going to put it in the back. I'll put it out front so it looks better. And that's my derivative. That's my derivative. Now this one here we've already done. This is basically sine x times sine x. I could use product rule, or I can go ahead and use the chain rule. Sine x times sine x. Very different than sine x squared. This is sine x squared. I take that 2 and I multiply it by the front. So that's going to give me 2 times sine x. Now the derivative of the guts is cosine x times cosine x, and I'm done. That's the derivative. Y prime equals. A little tricky here. Well, I don't like taking derivatives of radicals, so I'm going to rewrite that radical as an exponential function. I want to write that as a rational exponent. There's a hidden little 2 in there, so it's going to be x squared minus 2 to the 1/2, because what's in the bucket goes on the bottom. Now I'm going to use the power rule and the chain rule to find the derivative of this. The 1/2 goes times the front, so that gives me 1/2 times x squared minus 2. Don't forget to subtract 1 from that. I'm going to write 1 as 2 over 2. That gives me negative 1/2 times the derivative of the guts, which is 2x. Now this one I can simplify a lot further, okay? And I'm going to do that on a separate sheet of paper here. Basically 2x times 1/2 is just x. And this here, x squared minus 2 to the negative 1/2, that can be rewritten as x squared minus 2, and that can go downstairs to the positive 1/2. That can further be rewritten. And the final answer would be y prime equals x over the square root of x squared minus 2. And that would be my final answer for that one. Number 6, chain rule of e. Well, first thing I want to do is just write 5 times e to the 3x. Now I have to find the derivative of 3x and multiply it by the front. So the derivative of 3x is just 3. So my final answer is going to be y prime equals 15e to the 3x. We're on page 10 here. We're going to do something called implicit. That's derivatives with multivariables. We're going to be taking the derivative of this x squared, this y squared, and this 16. Could be kind of complicated. So the first thing I want to do is take the derivative of x squared, which is not too daunting. That's just 2x. But this is the strange part. When I take the derivative of y squared, it's going to be 2y and minus the 1. But now, because I'm taking the derivative with respect to x, I'm technically supposed to put dy dx behind it. I take the derivative of 16, and that's 0. So I don't like to write this dy dx when I'm doing implicit. I prefer to write it as y prime, as I have been. So 2y times y prime equals 0. Now, you must solve for y prime. Because in all the other problems, didn't we have it as y prime equals something? Didn't we have it as y prime equals something? Y prime or dy dx equals something? So I need to set this equal to y prime. I need to find out what y prime equals. So I'm going to subtract 2x from both sides. That would give me 2y times y prime equals 2x. And then I'm going to divide both sides by 2y. And that's going to give me y prime equals, it was actually negative 2x, negative x over y. And that's my answer. You could, if you want to, go back and rewrite that as dy dx, but most of the time you get away with just leaving it as that. Once again, implicit, I want to find the derivative of everything with respect to x. So this is going to give me 12y squared times y prime. Not y to the first, y prime. Plus 2x equals 0. Now I'm going to solve it for y prime. I'm going to subtract 2x from both sides. That's going to give me 12y squared times y prime equals negative 2x. And I divide everything, both sides, by 12y squared. And this is going to give me y prime equals negative x over 6y squared. And that's my answer for number 2. For this one, I'd like to use the power rule. So I'm going to rewrite this with negative exponents. So that's going to be x to the negative 1 plus y to the negative 1 equals 3x squared. I'm going to start to do my implicit differentiation. So this is going to be negative 1x to the negative 2 minus 1y to the negative 2. Don't forget, y prime, not y to the first, equals 6x. Now I have to solve this for y prime. I'm going to leave the negative exponents for now. So I'm going to add 1x to the negative 2 to both sides. So that's going to give me negative y to the negative 2 times y prime equals 6x plus x to the negative 2. Then I'm going to divide both sides by negative y to the negative 2. Divide this by y to the negative 2. And that's going to give me y prime equals 6x plus, I'm going to rewrite this as 1 over x squared over 1 over y squared. And no calculus teacher in their right mind will let you get away with that answer. So we're going to simplify it. And the way I'd like to simplify this is use the common denominator x squared, y squared. I'm going to multiply the top by that and the bottom by that. Technically, I'm only multiplying it by 1. And that's going to give me 6x cubed y squared. When I do this, times that, plus y squared, because the x squared cancels out with the x squared, all over x squared. And that should be my final answer. This one's a whopper because I have to implement the product rule inside of an implicit differentiation problem. So I'm going to start off, I'm just going to split that down the middle and label this as u and this is v. And then on the side, I'm going to do that work. So u equals x squared, v equals y, du, the derivative of x squared, equals 2x. The derivative of y, the dv, is just y prime, so it's not that big of a deal. Then it's u dv, so x squared y prime, plus v du, 2xy. I prefer to write it in alphabetical order. Plus 4y cubed y prime, don't forget I have to differentiate with respect to x, minus 3 equals 0. Now I have to solve this for y prime. So I'm just going to do some grouping, a little bit of algebra. That's going to give me x squared y prime plus 4y cubed y prime equals, add 3 to both sides, subtract 2xy from both sides. Now I'm going to factor out a y prime, but if you do this enough, you start to realize that when I factor that y prime out, I'll just be left with x squared plus 4y cubed. So I'm going to divide both sides by x squared plus 4y cubed. And that will be my final answer. So y prime equals 3 minus 2xy over x squared plus 4y cubed. Page 11, what we're going to do here is some higher order derivatives. What that means is that I want to find the first derivative, the second derivative, and the third derivative of this long expression. And we're just going to get started. The first thing I'd like to do is rewrite this with a negative exponent, because I don't want to have to do quotient rule. As we did before, it's a little complicated. So I'm going to rewrite that as just x to the negative second. And now I'm going to take the first derivative of that. So the first derivative is not too complicated. That's going to equal 20. X to the third, don't forget you minus 1. 2 times 3, that's 6x. And after I subtract 1, that's x to the first, but I don't have to write anything. And then this is just going to be plus 2. And then negative 2 times the 1 hidden out front is going to give me negative 2x. Subtract 1 to the negative third. Now I'm going to find the second derivative. And the second derivative, you just continue. 3 times 20, that's 60x squared. Plus the derivative of 6x is just 6. The derivative of 2, that cancels out, is just 0. Now the derivative over here is going to be negative 3 times negative 2. That's plus 6. X minus 1 to the negative fourth. And the third derivative. And that's going to give me 120, because 2 times 60 is 120. X, when I subtract 1 to the first, that goes away to nothing. And then I'm going to find this derivative, negative 24, because negative 4 times 6. X to the negative fifth. Now sometimes they might ask you to rewrite that as a positive exponent, so it would be 120x minus 24 over x to the fifth. And that would give me my third higher order derivative. Another higher order derivative, but this time I'm going to have to use the product rule. Okay, so I'm going to split that down the middle and call this first part u and the second part v. So that gives me u equals x cubed, v equals e to the x. We should start to like e to the x. The derivative of u is 3x squared. The derivative of e to the x, once again, is just e to the x. So the first derivative is going to give me u dv plus v du. U dv, that's x cubed, e to the x, plus v du. E to the x times 3x squared. Now I have to find the derivative of this. Hey, I'm going to have to use product rule again. But notice, the product rule of x cubed e to the x is already here. So half the work is done. So the second derivative is going to be this whole thing plus the derivative of the second part. X cubed e to the x plus e to the x times 3x squared. And now I'm going to split this down the middle and call that u and v. So u equals e to the x, v equals 3x squared, du equals e to the x, dv equals 6x. Now, udv plus vdu, udv is going to give me 6x e to the x, vdu is going to give me plus 3x squared e to the x. Now I have to add that to that, so this is starting to take up a little bit of space. So y double prime actually equals x cubed times e to the x plus e to the x times 3x squared plus 6x e to the x, 6x e to the x plus 3x squared e to the x. Oh my goodness. I have to find the third derivative now of this monster. And you can see where calculus isn't that tough. It's just a lot of algebra. It's just a lot of algebra. Well, I know that the derivative of this is already up there. The derivative of this is this entire thing. And then I have to find the derivative of this and the derivative of this. Let's see if I already have that anywhere. 3x squared e to the x, I do. So this is just going to be a lot of combining and expanding. I'm going to need another piece of paper. The derivative of that, using the product rule, is the same as the derivative of that. So I'm going to have x cubed e to the x plus e to the x times 3x squared. So that one's done. Now I'm going to find the derivative of the second term, which is the derivative of this second term, which I added over here. And that was this. So that's going to give me plus 6x e to the x plus 3x squared e to the x. Now I have to find the derivative of this. And I'm just going to do a little side work. U equals 6x, v equals e to the x, du equals 6, dv equals e to the x. u dv plus v du. I'm just going to add it over here and hope I fit it. It's going to give me 6x e to the x. 6x e to the x plus e to the x times 6, or 6 e to the x. Now, finally, I'm working towards the end here. I have to find the derivative of this, which I believe is the same as that derivative. So that's the red derivative. I can't fit it in one space, so I'm going to put a plus sign. And I'm going to add another plus sign, so I know I'm bringing it over here. And that derivative there was 6x e to the x plus 3x squared e to the x. And that's my third derivative. And you didn't think it was going to be that difficult, but it was a tough one.
Page 12, very brief look at calculus. What we're going to be finding today is called antiderivatives, or integrals if it has this symbol in front of it. That little curvy S is called an integral symbol. And these are not definite integrals because it doesn't have a little number at the bottom and at the top. We'll get to that a little later, but right now it's just called an antiderivative. Sort of like a derivative, but the opposite, working backwards a little. So let's just jump in and do an example. In a derivative, you would do 2 times the front number and then minus 1 from the exponent. For an antiderivative, instead of minusing 1 from the exponent, you add 1. And that would give me 3. Now, instead of multiplying by the coefficient, you divide by the exponent. Remember, you would multiply the 2 times the coefficient. Now you divide. So what's on top there is a 3. A 3 goes on the bottom. And there's your first antiderivative. Again, that's a hidden 1 there. I'm going to add a 1 to that because it's an antiderivative. That's going to give me 3x squared. Now I take that 2 and I throw it underneath. I divide. Plus, well, that's x to the 0. That would give me x to the first. And no need to throw the 1 underneath because it's implied. And now this is a little tricky because I'm finding the antiderivative. There might have been some number over here that I took the derivative of that disappeared. So we put plus c, meaning some constant, some number. And that's the first antiderivative. I could spruce this up a little, but I'm not going to.
I'm going to find an antiderivative of 5. Basically, it's 5x to the 0, so I add 1, so that's just going to give me 5x plus some constant number c. This one here, there's a hidden 1 up there, so I add 1, so that gives me 2x squared over 2. Notice that will simplify, and that's going to render just x squared plus c. For this one, 3x to the 4th, I'm going to add 1 to that, so it's going to give me 3x to the 5th all over 5 plus c. I add some constant c, and there's the antiderivative.
Finding the antiderivative, I add 1, so that's going to give me x to the 6th, and then I divide by that exponent, 6, plus 6x, I add 1 to the hidden 1 there, so that's 6x squared, over 2, I'll be able to simplify that, plus 2x, and plus c, and now I'm just going to simplify that middle term to give me x to the 6th over 6, plus 3x squared, plus 2x, plus c, and there's that integral or antiderivative.
Now for number 6 and number 7, some people might think that they want to change that to a negative exponent, and it's very logical thinking, but in this case, the antiderivative or integral of 1 over x is actually ln of x plus c. So that's just going to equal ln, and they put absolute value around this because it's not allowed to be a negative, plus c. And that's it. I hate to say it, you kind of have to commit that one to memory. And I often make the mistake of trying to put that as a negative exponent and finding the antiderivative by adding 1 to it. And the integral of e to the x, you probably already guessed this, it was going to be e to the x, but you have to add some constant c.
Well, after integrals, with just a little loopy s there, comes definite integrals. And this is called on the interval from 1 to 3. This is page 13 from A Very Brief Look at Calculus. And we're going to evaluate some definite integrals. The first thing you want to do is find the antiderivative of 2x. What's nice about this is you don't have to do the plus c. So there's a hidden one there, so that's going to give me 2x to the second. And when that's simplified, I got to put it over 2. You put that exponent underneath. That simplifies to just plain old x squared. Now I'm going to set up this notation from 1 to 3. Okay, and now I want to find out what the area is by evaluating this from the interval from 1 to 3. And that means I take this value squared and I subtract it from another value squared. And all I do is plug this value here into the first one and this value into the second one. 3 squared is 9. Minus 1 squared is 1, and my answer is going to equal 8. And that's my first definite integral.
Same problem, I'm going to now complete on this Casio. It will do it for you. You see it has an integral button right there. It's a wonderful button on this calculator. So I'm going to evaluate that integral from 1 to 3 of 2x. So I'm going to hit that button, and I'm going to type in 2 alpha x from 1 all the way up until 3. And I'm going to hit the equal sign. And bingo, it gives me the answer pretty rapidly, which is not that good in a calculus class because they usually want to see how you arrived at that answer.
Still working on number 1. A different way to do it is to graph y equals 2x. So I'm going to graph that equation y equals 2x. That means I begin at 0 and the slope is 2. I go up 2 over 1. I go up 2 over 1, up 2 over 1, up 2 over 1. And it says from 1 to 3. So I'm basically going to find the area underneath this line from 1 all the way up until 3. And notice that gives me a trapezoid. That shape there is a trapezoid. And the area of the trapezoid is going to be 1/2 height, base 1 plus base 2. So I'm going to find this area instead of using calculus, using geometry. So the height is 2, so I'm going to put 0.5 times the height 2, times base 1, which is 1, 2, 3, 4, 5, 6, plus base 2, which is 2. So that's going to give me half of 2 times 8, which is just going to give me 8, geometrically, number 1.
Number 2, I'm just going to find the antiderivative without doing any fancy lines. There's a hidden 1 there, so I add 1 to that, so that gives me 2x squared, and then I divide it by the exponent. That's going to simplify to x squared, or in the interval from 0 to 3, so it's going to be something squared minus something squared, and that something is, for the first one, is going to be 3. I take this 3 and I throw it in here, then I take this 0 and I throw it in the back there. 0 squared is 0, so my answer should be 9.
Let's test that on the Casio. Integral of 2 alpha x from 0 to 3. And yes, it equals 9.
I want to find this integral. First thing I want to do is find the antiderivative. So that's going to be 2x squared over 2 plus 1x, or just x, on the interval from 0 to 4. Notice the 2's simplify. So that's going to give me a double quantity. So that's going to give me x squared plus x on the interval from 0 to 4. And I'm going to set that up with a minus sign in between two quantities, because there's a little bit more involved to this one than just a single term. So that's going to be x squared plus x squared plus x, and now I'm just going to fill in those templates with the values on the interval from 0 to 4, so the 4 goes up front, here and here, and the 0 goes in the back there and there. 4 squared is 16, 16 plus 4 is 20, and then it's nice to see that this is just going to be 0, so my answer is 20.
Let's try it on the Casio. 2 alpha x plus 1 from 0 to 4, 20. Pretty rapid.
Okay, this is the trig function, and notice the interval of the integral is from pi over 6 to pi over 2 of 8 cosine x. Remember, the derivative of cosine, the integral of cosine is sine, not derivative. So I have to find the antiderivative of cosine, and that's going to be sine. So here we go. That's just going to give me 8 sine x, and that's the antiderivative on the interval from pi over 6 to pi over 2. So that means I have to evaluate it at these numbers. So it's going to be 8 sine of some number minus 8 sine of the second number. And what I throw in there is going to be this pi over 2 first, and this pi over 6 second. And that's where our unit circle comes into play. You remember this thing. So I need to know what the value of sine of pi over 2 is. The sine of pi over 2 is 1. So 8 times 1 is just going to give me 8. Minus 8 times something over here. Pi over 6. Sine of pi over 6 is 1/2. So 8 times 1/2. And that's going to give me 8 minus 4. So 8 minus 4 equals 4. And that's my solution to that definite integral.
Let's make sure I'm in radian mode. And yes, I believe I am. There's a little r there. I see the little r. And let's see how well it does with a trig function. Integral of 8 cosine alpha x, close parentheses, you have to be careful, from pi over 6 all the way up to pi over 2. And remember, my hand answer was 4. It's thinking, and there it is. It took a while to do it, but quicker than me doing it by hand and absolutely more accurate.
Page 14 of a very brief look at calculus. What we're going to talk about now is U substitution, or what some of us prefer to just state as U sub. And what this means is I can't readily find the integral or antiderivative of this, and I definitely don't want to do binomial theorem of this. So I'm going to use a little U substitution. I'm going to come over here and say, let U equal the guts. But once I do that, that's going to give me U to the 4th, but I can't keep the dx with the u there, so I have to differentiate this. So du, the derivative of u, is going to equal the derivative of this side, which is just going to give me 1 dx though. Now, I have du equals dx, so I can replace dx with du. Now, I'm just going to find the antiderivative of u to the 4th, and that's going to give me u to the 5th divided by 5 plus c. But what does u equal? We noticed that u equals x minus 5. So I substitute that back in to give me x minus 5 over 5 plus c. And there's my first u sub. Not too bad. Number 2 for u sub, notice now I have to multiply product and it's to the 3rd power. I definitely don't want to do binomial expansion of that and then multiply it by x to the 4th, so I'm going to use u sub. And I'm going to let u equal the guts, x to the 5th plus 17. So that's going to give me the integral of x to the 4th times u to the 3rd. But I got to make this a du, not a dx, so I have to take the derivative of both sides over here. So du is going to equal something dx, and that's going to give me 5x to the 4th dx. Notice I'm taking the derivative over here and the antiderivative over here. Now, I see I have an x to the 4th over there and a dx, so that x to the 4th is going to cancel out with that x to the 4th, and that dx is going to cancel out with that dx, but I'm left with this 5. So what a lot of people do is they throw it underneath and they divide both sides by 5, and that gives me 1/5 du equals x to the 4th dx. So now I have to take this 1 to the 5th du and bring it over here. Du, and oftentimes we put the 1/5 out front. And I don't really need that x to the 4th. It was canceled out here. It was canceled out with the dx there. So that just leaves me 1/5 of the integral of u cubed du. Now, I can find the antiderivative of that and then substitute that back in. Let's see, I add 1, so that gives me u to the 4th over 4, but I have to multiply this by 1/5 plus c. Now when I put the x to the 5th back in, that's just going to give me x to the 5th plus 17 in for u to the 4th power now, all over 5 times 4 is 20 plus c. And that was a little bit more involved u substitution. I have another u substitution problem, and I'm going to let u equal x cubed minus 1, but this time I have a definite integral. And this is actually a little bit easier if you look at it as a work-related problem. It's a little bit simpler to do this. I'm going to take the derivative of u over here, so that's du equals 3x squared dx. I can get rid of the x squared and the dx. They will eliminate, but the 3 will not. So it's going to give me 1/3 du equals x squared dx. And notice, that x squared dx will replace that x squared dx with a du. So I'm going to put u over here to the 4th with a 1/3 out in front, because I have this 1/3 out in front, of du. Doing everything I'm supposed to here. Now, I can go ahead and find the antiderivative of this and then plug that x cubed minus 1 back in, or I can rewrite the integral in terms of u. So I take that 0 and I throw it over there. For x, 0 cubed is 0 minus 1. So that's going to give me a new integral from -1 to, let me put the 1 here in, 1 cubed is 1 minus 1 is 0. Now I'm going to evaluate this definite integral in terms of the new interval. So, u to the fifth, I add 1, divided by 5, but don't forget I have the 1/3 out front, on the interval from -1 to 0. So now what I need to do is simplify this a little bit further. That's going to give me u to the fifth over 15 on the open interval from closed interval from -1 to 0. And now that's going to give me something to the fifth over 15 minus something to the fifth over 15. And the values I throw in those brackets or those parentheses is 0 or -1. Now 0 to the fifth is 0. 0 divided by 15 is going to give me 0 minus -1/15. So minus minus. Let's see, that's going to give me a positive 1/15 as my answer. Let's see how well we fare using technology.
On this problem. So my answer was 1 over 15, and let's see if we can achieve that using the Casio. So let me turn it on and hit the integral button, which is right here. And I'm going to type it in like it looks, alpha x squared times parentheses, alpha x to third power minus 1, close parentheses, to the fourth power.
Let's see how well we do with our calculator. I'm going to hit the integral button and type in alpha x squared times parentheses alpha x cubed to the third power minus 1, close parentheses, to the fourth power from 0 to 1. And let's see what we get. It should be 1 over 15. And there it is, 1/15.
All right, for number 4, I want to do u sub and let u equal 1 minus x, but I've already entered it into the calculator, and I'm going to hit equals. Now, if it's a radical function, it takes Mr. Casio a long time to figure it out. Sometimes I can do it quicker by hand than the computer can. So let's see here, I'm going to let u sub, so that's going to be u to the 1/5, because what's in the bucket goes on the bottom. Now I'm going to find the derivative of u over here, so that's going to be du equals -1 dx. The dx will cancel out with the dx, but the -1 has to go out front, and the du replaces. Now, I'm going to also reevaluate the interval. So I'm going to throw 1 in. 1 minus 1 is 0 for my new ending interval. And throw a 0 in over there. 1 minus 0 is 1. And now this is a little creepy because I'm going backwards. But the rule in calculus is if you flip-flop that and make it from 0 to 1, you have to put another negative in front. And notice that's going to give me positive now of u to the 1/5 du. Now I'm going to go ahead and find the antiderivative and evaluate it from 0 to 1. So I'm supposed to add 1. I'm going to add 5 over 5, so it's going to give me u to the 6/5 over 6/5 from 0 to 1. But I want to simplify that, so u to the 6/5 times the reciprocal of that. I'm going to put it out front. That would be 5/6 from 0 to 1. And let me enter that 5/6 times 1, that one, to the 6/5 power, minus 5/6 of 0 to the 6/5 power. Now this is going to equal 0, and this is going to equal 1. So 1 to the 6/5 is just 6/5. So that final answer is just going to give me 5/6. And notice the answer just came up on the calculator, 5/6. Now I want to see if that's the decimal equivalent. Notice it didn't give me the exact fraction. It gave me a decimal. So I'm going to see what I can do with my calculator here. 0.8333333. I'm going to overload my calculator. And usually if you do this on this type of fancy calculator, and there it is, it equals 5/6. So that's approximately equal to 0.833 repetend. 0.83 repetend. They're the same answer. So I'm going to let u equal 3x, which is the exponent up there. The derivative of u equals 3 dx.
For u sub, last one, what I want to do is let u equal x cubed. So I'm going to find the derivative of that. That's going to give me du equals 3x squared dx. I notice immediately that the x squared will cancel out and the dx will cancel out, but the 3 will not, so I'm going to divide both sides by 3. That gives me 1/3 du equals x squared dx, and as I said already, that x squared dx is just going to replace that x squared dx. I'm going to also reevaluate the interval from 0 to 1 and see what happens. When x equals 0, that's 0 cubed, u will equal 0. When x equals 1, 1 cubed, well, the interval didn't change. I'm a little surprised, but pleasantly surprised. Have to bring the 1/3 out front. And this is going to give me e to the u. du now. That du goes there. I'm going to find the integral of antiderivative of e to the u. And we like this. The integral of e to the u is going to be e to the u over 3, because of the 1/3, from 0 to 1. And let me plug that in. That's going to give me e to the first over 3 minus e to the 0 over 3. Let's recall that e to the 0 is going to be 1. So this basically is going to give me e minus 1 over 3. And let's see what that equals.
E minus 1 over 3 is approximately equal to 0.5728. 0.5728. 0.5728. Let's try this one on the Casio from the beginning. Integral of x squared times e to the x cubed from 0 to 1. And yes, it matches up. It matches up. But notice you have to use the calculator to get that decimal equivalent. Most teachers would want it in exact form.
Okay, page 15, very brief look at calculus. Limits at infinity. Before they were at a number or 0, now they're at infinity. And I'm going to do this one right in the book. The deal is, if you have the graph of y equals 5, the further right
You go on that graph at y equals 5, it's always going to approach 5. So your answer
limit as x approaches infinity of 5 equals just 5. Now, when I plug infinity into that, wow, 5 times infinity. Let's see what that's going to equal. Well, that's going to equal infinity. So the limit as x approaches infinity of 5x is infinity. Let's see what happens here. I plug infinity into there, and that for x, and that gives me infinity over 7. Well, infinity divided by 7 is going to give me a really big number, and that number is about the size of, let's see here, infinity. Now, this is really off the chain. As x approaches infinity, and it's kind of crazy, I have an 8 over a lazy 8, so that's going to equal 8 over infinity, and infinity is a really big number. So you could get a decimal point, really long decimal point, but if you were to round that decimal point to like the trillionth place, you'd still probably get 0. So any number divided by infinity is basically 0. Now this one, there's a lot of technical ways to do this and formal ways to do this, but this is a very brief look at calculus, and limits are a very important part of calculus, but I want to get through it as quickly as possible. I don't really need to look at these values back here as x goes to infinity. I just need to look at the highest degree on the top and the highest degree on the bottom, and I notice this is going to simplify to 5 over 4 over x, because the degree on the top is smaller than the degree on the bottom. Now when I plug infinity into the x, that's going to give me 5 over 4 times infinity. Now 4 times infinity is 4 times bigger than infinity, so 5 divided by that is going to go to 0. Now the degrees are the same for number 6. So basically when I forget about all these other degrees and just look at this, well, x over 17 is going to simplify with x over 17. So this limit is actually going to approach the number or the fraction 12 over 17.
Page 16, very brief look at calculus. We're going to discuss something called L'Hôpital's rule. Not El Hospital or Hospital, L'Hôpital. It's French, I believe, and one of my students gave me the correct pronunciation. Indeterminate form means if you get infinity over infinity when you plug a value in, or 0 over 0, and we've already arrived at that in another example. So first thing I'm going to do is plug this in, and that gives me 4. 2 squared is 4, and 4 minus 4, well, that equals 0. So, and then I plug the 2 in, that gives me 2 minus 2, and that equals 0, and that's indeterminate form. So I could factor it. That's a way of doing it, but I want to implement something called L'Hôpital's rule. And what that means is you take the derivative of the top, and the derivative of the top is 2x over 1. So that beat it up pretty quickly. And now I take the 2 and I throw it in. And 2 times 2 over 1 equals just 4. So by L'Hôpital's rule, and I think that's what that little H hat means. You put that there to let people know that you're doing L'Hôpital's rule. And it's a quick way of finding the limit of something where you get 0 over 0. So I throw a 1 in here, and that gives me 1 cubed minus 1, or 1 minus 1, so that's going to equal 0. And I put a 1 in there, 1 minus 1, well, that equals 0. So I'm going to implement L'Hôpital's rule. I'm going to take the derivative of the top, which is 3x squared over 1. I'm going to substitute the 1 in, and that gives me 3 times 1 squared over 1, which is just 3. So by using L'Hôpital's rule, I didn't have to factor that.
Number 3 here, this should be the limit as x approaches infinity. So we
can take a look at what happens when we plug that in. Well, we get e to the infinity over basically infinity, because x cubed is infinity cubed plus 2 times infinity, and e to the infinity is, I'm pretty sure I have that back here. The limit as x approaches infinity of e to the x is infinity. So this gives me infinity over infinity, which is indeterminate form. So I'm going to implement L'Hopital's rule. So let's see what happens when I do L'Hopital's rule. So I take the derivative of the top, which is going to give me e to the x, over 3x squared plus 2. Plug infinity back in, and once again, that gives me infinity over infinity, which is indeterminate form. So I'm going to implement L'Hopital's rule again.
Let's see what happens. That gives me e to the x over 6x. Plug in infinity, that gives me e to the infinity, which is infinity, over 6 times infinity, which is infinity. Right, so that gives me infinity over infinity. Let me try L'Hopital's again. Keep trying it. That gives me e to the x over 6. Now that will give me infinity over 6. Infinity over 6 is not infinity over infinity, nor is it 0 over 0. It is infinity, and that's my answer for that one.
A very brief look at calculus, page 17. Limits using a graph. And I'm going to say that this weird, strange graph is f of x. I know I can't designate any real equation to it because it's sort of all over the place. And instead of using my pen or marker, I'm going to use a pencil for this one. This means here the limit as x approaches -4 from both sides. So -4 is right here. So as x gets closer to -4 from both sides, I call this like a pimple popper. I'm coming from the left and I'm coming from the right. And I'm going to pop that right there at -4. And the value, y value at -4 right before I get to -4 is actually 1. So that answer is 1. Now the limit as x approaches -4 from the left, that's a left-sided limit, or a left-handed limit. I call it a left-sided limit. So as I get closer and closer to -4, approaching it from the left, the negative side, my y value approaches 1 again. Now I'm going to approach -3 from the right. So I'm going to approach -3 on the graph from the right. What y value am I getting closer and closer to? I'm getting closer and closer to the y value of 2. Even though I don't hit it, I get closer and closer to it. The y value approaches 2. Now, this is asking me, what is the y value when x equals 2? They want a coordinate, and the coordinate's going to be -2, 5. So that's going to give me a 5 there. Now, they want to know what the y coordinate is when x equals 0. When x equals 0, the coordinate is 0, 5. Whoa, 0, 5.5. Notice it's a little bit between it. So that's going to give me 5.5 or 5.5. Now, the limit as x approaches 1 from the left. As x approaches 1 from the left, I'm following along, and that's going to give me 4. Now, my limit as x approaches 1 from the right. As x approaches 1 from the right, that's going to give me a y value of 2. Now, the limit as x approaches 1 from both sides, from the left and from the right, notice they do not meet each other like over here. They met. They're just looking across the little hole there saying, hi, I'm over here. Hi, I'm over here. Here, they're too far away. So that limit, because they don't meet, is called DNE. The limit does not exist. And you might have heard that from the movie Mean Girls. That's what she meant when the limit did not exist. If she had a graph of it, she'd have seen it instantly and would not have had to have thought about it so much. The limit as x approaches 9 from both sides. Now I know the y value when x equals 9, the coordinate is 9 too, but the limit is 3 because it approaches 3 from both sides. What is the value at 9? Now that's the coordinate, 9, 2. 9, 2. This here is evaluated at 9. This is the limit as it approaches 9. A subtle difference. And this one here has a lot of interpretive question marks. The limit as x approaches 4 from the left and the right. Notice, it goes to positive infinity. It goes to positive infinity. This one went to 2 and this one went to 2. So the limit was 2. Some people will say the limit as this approaches 4, because it's positive infinity on the left and positive infinity on the right, the limit as x approaches 4 is positive infinity. Other people say it doesn't exist. I'm going to go with positive infinity. That's my take on it. Page 18, very brief look at calculus. We're going to use geometry now instead of integrals to find areas. And the first integral I'm going to find of this graph, f of x. Now, this is made up of many different graphs. This is actually x plus 3. This is y equals 3. This here would probably be y equals negative 2x plus 5. This would be y equals negative 3. This would be x equals 7. You know, you get the gist that I could have a whole bunch of different graphs tagged together. But I just want to say that this whole shape is called f of x. And it starts at negative 3 and ends way over here at 12. Ends way over there at 12, okay? From negative 3 to 12. And I want to find the combined areas, or individual areas. So from negative 3 to 0, negative 3 to x equals 0, I basically wish to find out the area of this triangle. So I could use the integral formula, or just the basic area of a triangle, which is 1/2 base times height. So 0.5 times the base, which is 3, times the height, which is 3. And the area of that triangle is going to give me half of 9, or 9/2, or 4.5. And that's about it. That's about it. Now I want to find the area from 0 to 2. From 0 to 2. X equals 0 to x equals 2. And that will be the area of this rectangle. That will be the area of this rectangle. And that formula is just base times height, or I can just count the squares. 1, 2, 3, 4, 5, 6. So that area is 6. I really like doing these. It's not that challenging if you understand the terminology that they're giving you. Now I want to find the area from 2 to 4. From 2 to 4. And again, that's a triangle. That's another triangle. And that's from 2 to 4. And the base of that triangle is 2, and the height of that triangle is 3. So it's going to be 1/2 base times height, 0.5 times 2 times 3. And that's going to give me just an area of 3. Area of 4.5, an area of 6, and an area of 3. Now, this is kind of strange. I want to find an area from 4 to 7. From 4 to 7. And notice it's below. It is below the curve. That's going to generate a negative area. I know that kind of goes against your intuition, but in the calculus, that would give us a negative area there below the x-axis. And that's actually a trapezoid. And the formula for trapezoid is 1/2 the height times the quantity of base 1, which would be 1, plus base 2, which would be 1, 2, 3. So I'm going to write that whole formula out. That would be 0.5 times the height, which is 1, 2, 3. Actually negative 3, but I'm just going to put a 3 there. Base 1, which is 1, plus base 2, which is 1, 2, 3. And that's going to give me 1/2 times 3 times 4, which would give me 6. Not really. It's actually negative 6. It's negative 6. That's going to take a lot to put your brain around a negative area. Now I want to find the area from 7 to 9, another trapezoid. But this time, I think we have to turn this trapezoid sideways to actually visualize base 1 and base 2. From 7 to 9, so if I were to turn this sideways, now you can see the trapezoid. The height is 2, base 1 is 1, 2, 3, and base 2 is 2. So that formula is going to be 0.5 times the height, which is 2, and base 1 plus base 2, 3 plus 2, is 5. So that's going to give me a total positive area of just 5. That area there is 5. Now, this is a quarter circle. This is a quarter circle. Got to do a little bit more geometry from our geometry rules. The area of a whole circle is pi r squared. The radius of this, now I'm going to find the area of this quarter circle from 9 to 12. So that means my radius is going to be 3. So pi r squared, that's going to give me pi times 3 squared, which is 9. But I have to divide that by 4 because it's a quarter circle. Now, if I type 9 pi over 4 into my calculator, I get 7.06. So I'm going to say 7.1. Or I'm just going to leave it as 9 pi over 4. And that'll be my answer for that quarter circle over there in the right end. 9 pi over 4. And that's the area I found for that. Now, for the last one, it wants me to find the area from negative 3 to 12. From negative 3, this area, all the way over to 12. And that's going to be the net area. In other words, I have to add up where they're positive and subtract where they're negative. So it tells me to round, and 9 pi over 4, I'm going to say was 7.1. And I'm going to add these up. I'm just going to do it in the calculator. So 4.5 plus 6 plus 3
minus 6, negative area, plus 5, plus 7.1, and that's going to give me 19.6 for my total net area. 19.6. Page 19, very brief look at calculus. We're going to be approximating areas using right endpoints. They sometimes call this numerical analysis. Excuse me. And what it says here is approximate the area underneath. I have y equals x plus 2. I didn't pick anything too harrowing, nothing curvy, straight line. By finding each of the 6 rectangles, there's 6 rectangles here, areas, and then find the sum. So I'm just approximating. I'm not finding the actual area. I'm just going to find the approximate area. And if you'll notice, when I made these right endpoints from negative 2 to 4, that the rectangles go a little bit above the line. So this is going to be what we would call an overestimate. An overestimate. All right, let's get started. It said by using right endpoints. So I split the interval up into 1, 2, 3, 4, 5, 6 equal rectangles. And then I chose the right endpoint to draw the rectangle for that particular approximation. And that's the right endpoint. And notice the last endpoint at 4 is there. Now, technically I should have had it on the interval from negative 2 to 4, inclusive. And like I said, that gives me 6 rectangles. Rectangle 1 has a base of 1 and a height of 1. Rectangle 2 has a base of 1 and a height of 2. Rectangle 3 has a base of 1 and a height of 3. Rectangle 4 has a base of 1 and a height of 1, 2, 3, 4. Rectangle 1, 2, 3, 4, 5. Rectangle 5 has a base of 1 and a height of 5. And rectangle 6 has a base of 1 and a height of 6. So I'm just going to find the areas of each of these rectangles and then add them up. I'm going to find the sum of those. So basically, you can make it look kind of technical with the sigma notation. And the first area is 1 times 1. And I'm going to add that. To the second is 1 times 2. I'm going to add that, and that's 1 times 1, 2, 3. 1, 2, 3. And the next one is 1 times 1, 2, 3, 4. 1 times 1, 2, 3, 4, 5. And 1 times 6. And I'm going to add those all up, and I'm going to get a total area of 1 plus 2, that's 3. 3 plus 3, that's 6. 6 plus 4 is 10. 10 plus 11, 5 plus 6 is 11. That's going to give me a total area of 21. Total area of 21. Not bad, using right endpoints on an interval from negative 2 to 4. Now I'm going to use right endpoints. Left endpoints. Over here I used right endpoints. Now I'm going to use left endpoints. And this is kind of, again, strange because it's on the interval from negative 2 to 4. Notice there's no real height to that rectangle. Now, if my graph was moved up a little bit, there would be a height, but this one has a base of 1 and a height of 0. And I'm going to alternate again so I can see the rectangles alternate. And yes, there are 1, 2, 3, 4, 5, 6 rectangles for this graph also. But notice there's a little gap this time. Over here, there's a little overage. On this particular problem, page 20, there's a gap. So instead of it being an overestimate, this one's going to be an underestimate. And let's find the areas. Let's add up the sum of the areas. We'll sum these up. So the base is 1 times 0, plus this base is 1 times 1, base times height, plus this base is 1 times 2, 1 times 2. I should actually be looking at this side because it's a left endpoint. So the next one is going to be a base of 1 and a height of 1, 2, 3, left endpoint. 1 times 3. Next one, base of 1 and a height of 1, 2, 3, 4, left endpoint. The last one, a base of 1 and a height of 1, 2, 3, 4, 5, again, only the left endpoint. Let's multiply and add these up. So that's 0 plus 1 plus 2 is 3. 3 plus 3 is 6. 6 plus 4 is 10, and 10 plus 5 is 15. So this area is going to give me 15. Okay? I was looking at the 21. I almost wrote it too. I wonder what the average of 15 and 21 are. So 21 plus 15 over 2, that gives me 36 over 2. 18 is the average. I wonder if that's going to help me out. Again, this time, I'm going to use midpoints, or the interval from -2 to 4, and find the area of each rectangle. Notice, the midpoint, starting at 2 and 1, is actually -1.5. If I threw -1.5 into that, I would get 0.5, because 2 minus 1.5 is 0.5. This height, the same thing. If I threw -0.5, the midpoint, into that, I would get the height as 1.5. So I'm going to add up these areas. I'm going to add these areas up. And this base is 1, but the midpoint is at 0.5. So that's going to be 1 times the height of 0.5. Base is 1 times the height, which is 1.5.
Base of 1 times the height, which is 2.5. Add them up. Base of 1 times the height, which is 3.5, to that midpoint. 1 times 3.5. Base of 1 times the height of 4.5. And the last one, base of 1 times the height of 5.5. Because I have all these decimals, I'm just going to use the calculator. 0.5 plus 1.5 plus 2.5 plus 3.5 plus 4.5 plus 5.5. And let's see what that gives me. Notice, the midpoint gives me the average. The midpoint gives me the average. The sum is 18. I'd like to know if that's an accurate approximation. It's probably pretty close. Page 22. A very brief look at calculus. It's the same curve, or line if you want to call it that. X plus 2, on the interval from -2 to 4. Notice, I'm just going to find straight up the area of this triangle with a base of 6 and a height of 6. So for number 1, I'm just going to use the area formula, which is 0.5 times 6 times 6. And that's going to give me 36 cut in half, 18. That is, without a doubt, the exact area. This is an approximate, but it just so happens to be exact. Now I'm going to use the integral. Notice, if I have the integral process, I don't even need a graph. I can just find the area by using the calculus. So the antiderivative of x plus 2 is going to give me x squared. Don't forget you have to divide by that exponent. Plus 2x. I'm dividing by that exponent, but it's over 1. On the closed interval of -2 to 4. So now I'm going to evaluate it on this interval, the antiderivative. So that's going to give me something squared over 2 plus 2 times something minus something squared over 2 plus 2 times something. And what I put in to the first one is the 4. So I place the 4 in there and in there. And when I place it in the bottom one, the back one is the -2. So in the back I put a -2 and a -2. And now I'm going to evaluate this. Realize the exact area using geometry is 18. 4 squared is 16. 16 divided by 2 gives me an 8 plus 8 minus this quantity over here. Let's see what that's going to give me. -2 squared will give me 4. 4 divided by 2 is 2. 2 times -2 is -4. 8 plus 8 is 16. 16 minus -2, that's going to equal an exact area using calculus of 18. Exact area, approximate area, overestimate, underestimate. The average of the over and under gave me a very good approximation.